Hi, so hello everyone. Now that we have a grasp of the basics of electrical quantities, I will now introduce to you circuit analysis. The objectives of this lecture is to define what a circuit is and identify different structures found in an electrical circuit. Provide what we call VI characteristic curves of different elements found in electrical circuits. And these VI characteristic curves actually, let me just highlight that. Uh, so the VI characteristic curves actually are present in all electronic devices. And at the end of this lecture, you will be able to perform DC circuit analysis using what you've learned in the previous meeting, Kirchhoff's voltage law, current law, and Ohm's law. So actually, you have a circuit representation. The actual circuit is this physical system right here. Can be translated into what we call a schematic diagram. I'm sure you're already familiar with this. So this is your battery right here, and this is its circuit representation. This is your switch. If you push it, so if you push it, the switch will close. Okay, and finally, this because the switch is closed, current is able to flow across the circuit and powers up the light bulb, as you can see here. The conventional current flow is from, remember, it's from negative to positive because the conventional current is positively charged particles. But in reality, the actual current flows from positive to negative in a battery because electrons flow, and these electrons are negatively charged particles. So they flow in an opposite direction of your conventional current flow. For all intents and purposes of this lecture and all circuit analysis, we assume that the conventional current flows. We assume a positive charge flowing across your circuit. So therefore, um, it flows from the negative to the positive of a battery. So for example, this is your power system. Can be modeled by this complicated circuit right here. So don't worry about all these. This will be discussed as we go along triple E tree. So this is your generator, and this is your transmission line. Can be represented by this circuit right here. So the convenient thing about circuits is they have representations, and we can actually simplify bigger circuits into smaller circuits for easier analysis. So if you look at this power system right here, it's actually a very big circuit, but we can actually represent it in smaller circuits, as you can see here. So another example of an electronic system is this, just a simple light bulb, which is actually composed of a lot of components, as you can see here. And these are the parts of the light bulb. And each of these parts can be represented by a circuit interacting with one another. So the electrical network, let's go back to simpler circuits. The electrical network is an interconnection of electrical components. And the circuit is a network that has a closed loop, giving a return path for the current. So the difference between a network and a circuit is that the circuit is a closed loop. All right? Okay, so sorry. Okay. So let's go back to the abstract form. We have circuit elements. Okay. A circuit element is the mathematical model of a physical device. So basically, it could have a potential difference from its nodes right here. So plus minus, there's a voltage, and current can pass through the element. A simple circuit element in circuit analysis, these are the basic units that cannot be subdivided. So let's go back to the figure right here. Actually, these are already systems, as you can see here. and within them, it can still be broken down into components, and that is your general circuit element. So a general circuit element actually is composed of or represented by one or more simple circuit elements. For example, a DC machine. So we'll more on that in a later lecture. So we'll focus more on the simple circuit element right here. So any circuit element, sorry, any element or any device can consume voltage and current will flow across it. So let's classify these elements in terms of power consumption. An active element is capable of supplying power to other elements. But an active element can also consume power. So take note of that. A passive element always consumes energy, never the other way around. So it just basically the current flow is always from your positive to your negative. An active element can have current flow from negative to positive or vice versa. You do well to remember that. So next is your independent voltage source. This is an active element mainly because the current normally flows from your negative to positive, or the current can flow from your negative to your positive, which is represented by these three figures right here. For this sign right here, this is your AC voltage source. This is the representation of a battery, and this is your general voltage source. And its voltage current characteristic or VI curve is represented by a straight line. What does this mean? It means that for any value of current passing through, positive or negative, its voltage stays the same. So this is your independent voltage source. So the voltage stays the same regardless of current passing through it. And that's it. This is your independent voltage source. An independent current source is the opposite. So it's represented by this straight line right here. What does it mean? It means that for any voltage drop on this current source, its current, the current across that current source stays the same. So this is your DC current source. All right. So when we say DC, it's a constant voltage or a constant current, which is different from AC. We'll discuss more on that later in the semester. So let's just focus more here on DC. So again, regardless of voltage across this element right here, it could be negative voltage or positive voltage, the current stays the same. So the current is constant at the value Is. Okay. So next is the controlled sources. Basically, the source quantity is determined by a voltage or current in some other location. Take note, it's some other location in the system under consideration. So it if this is represented by a diamond in schematics instead of your usual circle or oval shape circuit element, it's represented by a diamond. So a plus minus right here means it's a dependent voltage source, which can be controlled by a current or a voltage. So these are the classifications of that. There's a voltage controlled voltage source and a current controlled current source. And the same is true with a current source right here. It can be voltage controlled or it can also be current controlled. So more on this as you solve more problems. So next is from your sources, we have now your resistor. A resistor is a passive circuit element, which means it always consumes power. That's why in a resistor, always, the current always flows from positive to negative. That's the natural flow of your current, correct? Since your current is consists of positive charges, see right here, current consists of positive charges, therefore, um, across a resistor, a voltage is developed from the flow of your positive charge to your negative charge. The voltage will always be um, where the current enters, that's the positive, and where the current exits the resistor, that's your negative. So your voltage drop is always from here to here. And to get the voltage with respect to the current passing through, there's actually a linear relationship between them across a resistor. So this is the equation for your this is the VI curve of your resistance or your resistor, and that is defined by the Ohm's law actually. So if you have a VI curve, the slope of the line between your voltage and current is R, as you can see here. So the more current that passes through the resistor, the more voltage it has. So that's actually defined by the Ohm's law anyway. So the power consumed by a resistor is equal to this equation right here, which is defined by the resistance. So if you have a given current across a resistor, you can actually get the power immediately using this equation. Okay, so some special cases of resistance. A short circuit is a circuit element with resistance equal to zero. If the resistance is zero, it should not have any voltage at all. Any current can pass through, its voltage is still zero. You can never have a voltage across a wire or a short circuit, because if you have a voltage, the resistance is zero, then the current will be V divided by R, any number divided by zero, that is infinity. Okay. An open circuit is the opposite thing. The current is zero for an open circuit. If the current is not zero, then the voltage must be very high. So it is actually infinite. So the resistance of an open circuit approaches infinity. So there's always no current across this across these terminals right here, which is an open circuit. Okay, so for example, identify the circuit elements in the following circuit. Okay, so from here on, you can pause the video before I reveal the answers to you, or you can just proceed. Can control you while you watch this video anyway. So let's look. So this is an example of a circuit. The voltage sources are these. So voltage source, voltage source. This one is a current source, three resistances, and what is this? It's a diamond, so it's a dependent voltage source. It's a voltage source because it has a polarity right here, and it's controlled by a variable Vx, which is the voltage drop across this 16 ohm resistor right here. Therefore, it's a voltage controlled voltage source. And this voltage right here, plus minus Vx, depends on the current across this resistor right here. More on that later. So next is we'll look at the DC machine. So a DC machine model can be modeled by this circuit right here. It has a voltage. If it's a DC machine, then the voltage is constant. So that's E sub C. And there's some armature resistance right here, and this is the field resistance, which defines the torque output of your machine. And because of that, there's a voltage developed at the terminals of the machine right there. And this one big element right here represents this one big block right here actually represents just one DC motor. Okay, so the structure, these are just definitions. Okay, so let's go by one. Branch is any portion of a circuit with two terminals. It may consist of two or more circuit elements. A node is a junction. So it's where two or more branches connect. So it could be, there you go. So this is one node, okay? A junction of two or more branches connect. So a path is a collection of branches, a movement through the network, wherein no node is encountered more than once. A loop is any closed connection of branches. So a closed path, etc., etc. A mesh is a loop that does not contain any other loops. The simplest form of a loop, actually. And finally, wires are ideal conductors, where each part is equipotential or has the same voltage. So what happens if electrons move across these, or if charges move across these wires, then the voltage across that wire is zero, or the voltage difference across that wire is zero. Therefore, your electron does not lose any energy at all. So the voltage here is equal to zero. There you go. Okay, so example of a circuit branch is this. So one branch is just from end to end. It has one path only. Does not branch out into other paths. That's just it. A node is anything that is actually just a short, or a just a wire. So the node is anything that does not have any circuit component. A loop is basically just one path that is closed. So for example, this outer loop right here is a closed path. This inner loop is a closed path. This inner loop here has a closed path. If you go through here, then go here, then here, it's actually one loop. So if you go through here, then go up, go back, go here, and back here, that's also a loop. A mesh is a special type of loop wherein there are no other loops within that mesh. As you can see here, it's kind of the simplest form of a loop. So if you add this loop to this loop, you'll actually create this loop right here. So that's already one loop, but it's not a mesh anymore. So the mesh here is what is within that bigger loop. And it's the simplest form of a loop. It does not cross any branches at all. Okay? So a special type of ground, or ground node, is actually a reference. It's associated as the node where the potential is zero. So that is what we call a reference node. In any circuit, you can actually set one node to be 0 volts. And the voltage, which is the potential difference between two nodes, will not change. This will be an important factor, or an important concept as we go along with circuit analysis. So if you look at this circuit right here, we set the node E, which is this big node right here. So it does not have any elements. We set that with a voltage of 0. Another way of doing this is, well, we can actually set C to 0, and all the values of A, B, E, D will change, but the difference VA minus VB, VE minus VC, VB minus VC will not change. So we only set a reference node to 0 volts to simplify our calculations. So we go now to circuit analysis. It's the process of determining relationships of voltages, currents, power, and other parameters in a circuit. A DC circuit is the analysis of a circuit with constant voltage or constant current sources. So basically, there are no changing elements, or no changing voltages and currents within that circuit. Therefore, everything is constant. So for example, let's look at this circuit right here. Okay. So for this circuit, we these are the steps on solving that. We need to find V2 and V3 using KVL. So we can compute for I1 and I2 using KCL, and calculate the power of elements A and C, etc., etc. So let's do that. Let me zoom in. There you go. Nope, too zoomed in. There. Okay, so first is you need to find V2 using KVL. So let's use this inner loop right here. There you go. This inner loop will get KVL. So from negative to positive, that's positive 10 volts. So that's 10. Sorry. From positive to negative, that's negative minus 4. And V2 is said to have a polarity of this. So that would be from positive to negative, you get minus V2. And that is equal to 0 because you've entered one loop. You have gone back to the same point. Okay, now we can solve for V2. Just transpose V2 and you'll get 6 volts. Quite easily done. Next, you'll solve for V3. Let's use this loop right here. From this loop, you'll see that the voltage at V2 now, you enter the negative to the positive. So V2 becomes positive in the equation. And for V3, you enter the positive and leave in the negative. Therefore, V3 is negative, and that is equal to 0. And you'll get by transposition V3 equal to V2, which is 6 volts. There you go. So you can actually get V3 without solving for V2. You can use the outer loop right here. Oops, sorry. And there you go. You can use the outer loop right here and you can still get the same V3 answer right here. And let's try that. So you enter negative to positive 10 volts. Minus 4 volts. You enter positive to negative. Then minus V3. Enter positive, leave negative. And it's negative. Equal to 0. And you can now solve for V3 by transposition and simplification. It's also 6 volts. Next is you solve for I1 and I2 using KCL. So at this branch right here, at this node right here, I1 enters and I2 leaves. And there's another current right here where your zero point 0.8 ampere current leaves. Okay, so at this node right here, some current 2 amperes enter and some current I1 leaves and no other current can be found at this node right here. So we can use this node first. You have the current going in equal to the current going out. So again, that's KCL. There's 2 amperes going in and I1 going out. Therefore, at that point of the circuit, 2 amperes equals I1. So that's actually the answer for I1. For this node, there's I1 going in, I2 going out, and some zero point 0.8 amperes going out. So you can now solve for I2 using KCL. So that's I1, all the current going in is just I1, and plus the sum of the equal to the sum of the currents going out. That's I2 plus zero point 0.8. So we can now solve for I2. Wait. Oh, there you go. There you go. So the current going in is I1, and that's equal to the sum of the currents going out. That's I2 plus zero point 0.8. You can now solve for I2 by just transposing uh, zero point 0.8 to the other side, and you know I1 is 2 amperes, so that's I2 equal to 2 minus zero point 0.8. That's 1.2 amperes. Quite easily done. You're done with number 2. Number 3, calculate the power of elements A and C. Identify if it's supplied or consumed. So element A, your current flows from negative to positive. So the power, across A, oops. So the power across A is equal to the voltage across A times the current across A. So the voltage across A is 10 volts and the current is 2 amperes. Therefore, you'll get 20 watts of power. How do you know if it's supplied or consumed? We've talked about this. If the current leaves the positive node, as you can see here, the current flowed from the negative to the positive, it's against the natural flow of things. Therefore, your electrons, or sorry, your charges are being energized at this element right here. Therefore, this element gives energy to the electrons. It's supplying power to the circuit. Therefore, this is a supplied power. And for element C, right here, so the element C here has a voltage V2, which is solved earlier. That's 6 volts. So element C, the power across C is the voltage across C times the current flowing through C, which is 6 volts times the current that we have solved is I2, so that's 1.2 amperes. So sorry, let me just check. There you go. So that's 1.2 amperes, and that is equal to 7.2 watts. Is it supplied or is it consumed? So you can see here the current here flows from positive to negative. Therefore, it consumes power since the positive charges from this current flows in the natural state of things. Therefore, it releases some of that energy in element C. Therefore, element C is consuming that power supplied by the energized electrons. So it's consumed. Okay. So finally, number 5, the circuit was used for 30 minutes compute for the electrical energy of element A. So how do we get the electrical energy of element A? So the electrical energy of element A, how much electrical energy it supply, is just equal to the power across A times the time uh, while it was running. So that's equal to the power, 20 watts, times 30 minutes. So let's just put the units. So that's 20 watts or 20 joules per second times 30 minutes. Sorry, there you go. And for 1 minute you have 60 seconds. So it's just dimensional analysis from here on out. Cancel the minutes, cancel the seconds, you'll be left with joules. And from here, you can see that there is 3,600 joules consumed, sorry, supplied energy to the circuit. So this is your answer in number 4. Okay, next. Sorry. So DC circuit analysis number 2, a DC generator will be used to supply the power to an electric stove right here. The equivalent circuit of the DC machine is shown below. What is the voltage across the terminals of the DC machine when the stove is not yet connected? So right here we have 125 volts, and if the stove is not connected yet, then the current IL here is 0. So let's work around that circuit. So in here, IL is equal to 0. Therefore, if we take the KCL at this node right here, the current going in is IA and the current going out is IF. Therefore, IA is equal to IF since IL is equal to 0. And now the next part is you will do KVL across this loop right here. So remember that for a resistor, the terminals, or sorry, the voltage polarity will always be defined by the current flow. So given the current flow is from here to here, the terminals would have this polarity right here. The current always flows from positive to negative across a resistor. And also the same in this resistance right here. Let's call this VA. And let's call this VF. So if we do KVL across this loop, we'll get 125 minus IA minus VA minus VF. How? So that's from negative to positive, positive 125, positive to negative, negative VA, and positive to negative, negative VF. And you'll get equal to 0. So by Ohm's law, we get VA equal to IA times 1 ohm. And also the same Ohm's law right here, that is equal to IF times 50 ohms right here. That is equal to 0. Now given that IA is equal to IF, we can now substitute the variables from here minus, IA times 50 ohms, and that is equal to 0. And this equation will now transform if we transpose these two uh, terms right here on the other side and add them, since they both have IA as a variable. We get 125 equals 51 IA. I can now solve for IA, and IA is some value 125 over 51. So I won't simplify that anymore. Okay. Now we want to know what's the value of VT. So the value of VT can be determined by, well, there are two ways. For one, we can use KVL on this loop, this loop right here. So KCL on this loop, and we get from negative to positive, that's VF. Okay, so let me just type that. So negative to positive, that's VF. Positive to negative, negative VT. And now we're back on the same point, therefore that is equal to 0. So simplifying that, we get VT equals VF. There you go. VT is now equal to VF. What is the value of VF? Well, we can use Ohm's law for that. That's equal to IF times RF, which is 50 ohms. Oops, there you go. So that's IF times 50 ohms. We get VF, or VT, is equal to IF is equal to IA, and IA is this value right here times 50, and you'll get, well, the answer is already there, 122.55 volts. So we can actually use a calculator to verify that. That's 125 times 50 divided by 51. Yes, so that's 122.55 volts. Next, letter B, assuming that the stove can be modeled as a resistor with 62.5 ohms, find the voltage across the generator when the stove is connected to the generator. So the added twist here is now there's a additional resistance. It's not open anymore. It has a 62.5 ohm resistance. So IL now is not equal to 0 in this case. Okay, so we have a VT right here. We have set VF and VA, and we can still use the same techniques to solve for the circuit. Right, let me just erase all ink. There you go. Okay, so let's start over. So you have 62.5 ohms right here. So 62, sorry, let me fix that. That's really bad handwriting, would you agree? Anyway, so 62.5 ohms of a stove. So first things first, we'll have to set up the equations. So you have IA, IF, and IL. We have three unknowns. And so we need three equations to solve the three unknowns. So first, KCL at this node right here. The sum of the currents going in equal to the sum of the currents going out. So that is equal to IA equals IF plus IL. That's equation 1. Equation 2 can be, you can use this loop right here. So you use this loop, and we set the VF to have this polarity right here, defined by the direction of the current. Also VA right here. There you go. So if you do KVL on this loop, you get what? VF, negative to positive, minus VT equal to 0. That's VF minus VT equal to 0. However, our three unknowns is defined by IA, IF, and IL. So we need to define this equation by the three unknowns. So by Ohm's law, this VF becomes IF times 50, and the VT becomes, since this is 62.5 ohms, becomes IL times 62.5, or 62.5 IL equal to 0. So this is our second equation. Third equation can be defined by this loop. So this loop, let's look at it. 125 positive, flowing from negative to positive. VA is here, positive to negative. So it's negative VA, which is IA times 1 ohms. So that's minus IA. And finally, your VF, again, 50 times IF. So that's this one, minus 50 times IF, equal to 0. So we have now our three equations and three unknowns from this three right here. Okay, so how do you solve this? Well, actually, you can substitute IA to this. So let's do that. Substitute this to this. Your equation becomes 125 equals, so I just transpose this to this side, becomes IF plus IL minus 50 IF. And it becomes 125 equals negative 49 IF plus IL. And the other equation is 50 IF, sorry, 0 is equal to 50 IF minus 62.5 IL. So you're left with two equations and two unknowns. So if we multiply this equation at the top by 62.5, sorry, 62.5, so what do we end up with? So 125 times 62.5, that's 7812.5, and 62.5 times 49, you'll end up with 3062.5, and you'll have 62.5 right here. So we add these two equations right here. If we add them, that's 7812.5 equals, so you add this to this, okay? So you add this to this, you'll get negative 3012.5. So is it correct? I sub f. And finally, you'll get your I sub f, 7812.5 divided by, sorry, 7812.5 divided by 3012.5. So that is 2.593 amperes. So IF is equal, oops, IF is equal to negative 2.593 amperes. So let us recheck everything. So the first equation is defined by this. IA is equal to IF plus IL. So IA, current going in, equal to the sum of the currents going out. Okay. So IA equals IF plus IL. That's correct. Second equation defined by the loop here. So that's VF equal to VT. And VF is equal to 50 times IF. VT is equal to 62.5 times IL. And that is this equation right here. And finally, we have this equation right here. So that's 125 minus VA minus VF. And you have this equation right here. Oops. This should be plus 50 IF. And that is my mistake. So this should be positive 51 IF times 62.5. So there's an error in my calculation. There you go. It should be 3187.5. See how an error can actually have drastic effects on your calculation. So 3187.5, you add this to this, you'll get positive 3237.5. There you go. And there, you'll get your final answer will be 7812.5 divided by 3237.5. So it's 2.4131 amperes. That's not the final answer yet. So we want to know the voltage at the terminals, which is equal to the voltage across your resistor right here. And that is equal to IF times the resistance 50. So just multiply 50 to the answer. And this is the final answer, 120.6564, which corresponds to this answer right here. Okay, next is the answer here, letter C. How much power will be supplied by the generator to the stove? When we say power supplied by the generator, we mean what is the power supplied by this big block right here. Okay? What is the power supplied by this big block right here? So think of it as a general circuit element. Let's go back to that slide. Think of it as this lump right here. So it can absorb or it can supply power. So that one big box right there at the end, there you go, supplies power to the stove. So what is the power then? How do we calculate that? So let me just erase everything first. There you go. So this DC generator actually outputs some current IL to the stove right here. So it seems like the current is flowing from negative to positive on this terminal right here, going out into the stove. Therefore, this big block right here generates power actually. So it supplies power. How do we compute that power? So the power is now equal to this voltage right here, VT, times the current IL. So first we need to solve VT. VT is what? Equal to VF, which is 120.66 volts. And next is IL. What is IL? So we go back to this equation right here. Here, there you go. You can solve for IL using this equation. So IL in this case is equal to 50 over 62.5 times IF. So we can calculate that. 50 divided by 62.5 times IF, 2.4131. That's 1.9305. So IL is equal to 1.9305. And we can substitute it here. 1.9305. So multiply that with 120.66, you'll get 232.93 watts of power. So that's the power supplied by the generator into the stove. Alternatively, it's the power consumed by the stove from the generator. Okay, to summarize, from this lecture, I have provided a formal definition of an electrical network and an electrical circuit, introduced different DC elements, enumerated the structures found in an electrical circuit, and the most important part is we used KCL and KVL, Ohm's law to perform DC circuit analysis. So if you have any questions, do not hesitate to leave a comment. We can discuss on in Facebook using the threads, and I'll see you next meeting.